So for number 6, we want to prove all these statements here. So let's begin with item A. So A, we want to prove that for every natural number n, 1 over n is less than or equal to 1. So let's begin with this. And we're going to say let n belong to the set of natural numbers. Well, if this is the case, then n is greater than or equal to 1, right? That's just a direct consequence of it being a natural number. So we're going to say dividing both sides gives us n over n is greater than or equal to 1 over n. So it simplifies to n over n is just 1. So that's going to be 1 is greater than or equal to 1 over n. And so if 1 is greater than or equal to 1 over n, it means that 1 over n is less than or equal to 1. And so we can say our conclusion, therefore, for all n belonging to the set of natural numbers, 1 over n is going to be less than or equal to 1. So that's it for item A. Now let's do item B. So B, it says there is a natural number m such that for all natural numbers n greater than m, 1 over n is less than 0.13. So we're going to do let m n belong to the set of natural numbers. Suppose that n is greater than or equal to m. Okay. And then now we want to prove the existence of a natural number, so we just have to produce a natural number in that universe. So we're going to say let m is equal to 13. So we have produced a natural number, right? So we can do that. And then we have then that, actually, let me do it the other way. So if n is greater than m, it means that 1 over n is going to be less than 1 over m. So this is true. And now we're going to say let m be equal to 13. So what we've gone ahead and done is we've produced an object in the universe. And then, so 1 over n is going to be less than 1 divided by 13, which is equivalent to 1 over n is less than 1 divided by 13 is 0.13. So what we've done here is we have said, therefore there exists an m belonging to the set of natural numbers such that for all n belonging to n, it means that if n is greater than m, then if n is greater than m, then 1 over n is less than 0.13. Yeah. So that is it for item B. So just to recap, therefore, there exists an m belonging to the natural numbers such that for all n belonging to the natural numbers, if n greater than m, it means that 1 over n is less than 0.13. Okay. So let's go to item C, and I'm going to try to erase all of this at once. It's not letting me, so afraid we're going to have to erase it individually. All right, let's go to item C. So item C says that for every natural number n, there is a natural number m such that 2n is less than m. So we're going to say here, for C, we're going to say for every natural number n. So let n belong to the set of natural numbers, and then what do we have here? There is a natural number, yeah. So maybe I'm going to say let m belong to the set of natural numbers, right? So what we have to do here is we're going to have to produce a natural number m. We have to show that it exists, right? So we're going to say let m be equal to 2n plus 1. And we can do this because if n is a natural number, then 2n plus 1 is also a natural number, right? So we have here, we have that 2n is less than 2n plus 1, right? And so because of this, so 2n is going to be less than m, because m is 2n plus 1. And that is it. So for this one, therefore, or for all natural numbers, so for all n belonging to the set of natural numbers, there exists an m belonging to the set of natural numbers such that 2n is less than m, right? And we have shown that that is the case if m is 2n plus 1. Okay, so that is it for item C. Let's do item D. So for item D, we have that we want to show that there is a natural number n such that for every natural number n, 1 over n is less than m. So we're going to say D, let m n belong to the set of natural numbers, right? Well, if they belong to the set of natural numbers, then m is greater than or equal to 1 and n is greater than or equal to 1. So we have shown in part A that this here is true for a natural number n, so we're going to use that. So we're going to say by part A, we have that 1 over n is less than or equal to 1. So what we have to do here for D is we have to show that there exists a natural number m such that for every natural number n, 1 over n is less than m. So we're going to produce that natural number by showing that it belongs to the universe. So we're going to say let m be equal to 2, which we can do that, right? Because 2 is indeed a natural number. So we have that. We have that 1 over n is less than or equal to 1, which is less than 2. So 1 over n is going to be less than 2. Therefore, 1 over n is less than m. So we have shown what we need to show, and our conclusion is going to be, thus, there exists an m belonging to the set of natural numbers such that for all n belonging to the set of natural numbers, 1 over n is going to be less than m. And that is it for item D. So now we're doing item E, which is there is no largest natural number. What we're going to do here is we're going to prove it by contradiction. So for E, we're going to say let m n belong to the set of natural numbers, and suppose that n is the largest natural number. Okay, so once we have supposed this, we're just going to say let m be equal to n plus 1, which we can do this because n plus 1 is a natural number, right? And so we have that m is natural since the natural numbers are closed under addition. This just means that whenever I add natural numbers, I'm also going to get a natural number, right? Note that n plus 1 is greater than n, so m is greater than n, which is a contradiction. Okay, so the conclusion is going to be, therefore, there is no largest natural number. There is no largest natural number. And that is it for item E. So similarly for item F, it's asking us to prove that there is no smallest positive real number. And we're going to prove the same way, which is by contradiction. So in this case, we're just going to say let x, y be positive real numbers, right? So let x, y belong to the set of real numbers. Let x greater than 0, y greater than 0, and suppose that x is the smallest smallest, I'm just going to say positive real number. Yeah. So we're beginning by assuming the opposite, and now we're just going to say let y be equal to x over 2, which we can do that because x over 2 is still going to be positive, and it's going to be, actually, well, let me do this differently. So note, once more, making the same mistake, note that x over 2 belongs to a set of real numbers, and x over 2 is greater than 0. So we're going to say let y be equal to x over 2. We have that x over 2 is going to be less than x. So y is less than x, which is a contradiction. And then the conclusion would be, thus, there is no smallest positive real number. There is no smallest positive real number. And that is it for, oops, I should have changed that. That is it for item F. Now, so for item G, we have that for every real number epsilon greater than 0, there's a natural number m, such that for all natural numbers n greater than m, 1 over n is less than epsilon. So what we're going to do here is we're going to say for G, let epsilon belong to the set of real numbers, and let epsilon be greater than 0. So 1 over epsilon is going to be greater than 0 as well, right? And what we're going to say, let m, n belong to the set of natural numbers. Let m be equal to the floor of 1 over epsilon plus 1. Now, what does this mean? The floor operation just means like take the integer part. So if we know that 1 over epsilon is positive, so say that 1 over epsilon is like 0.23, then the floor of that would just be equal to 0. Or if it were 1.23, the floor of that would just be equal to 1, and so on. And so because the floor of 1 over epsilon is going to give back a natural number, right? Or 0, because it is 1 over epsilon is positive, so we have that m is an integer, right? Because m is at least 1. Okay, so once we have this, we have that note that m is greater than 1 over epsilon, right? And the reason that it's greater than 1 over epsilon is because we took the integer part. So 1 over epsilon is the integer part plus the decimal, whereas m is the integer part plus 1. So m is definitely greater than, right? Thus we have that 1 over m is going to be less than 1 over epsilon. So 1 over m is going to be less than 1 divided by epsilon is just less than epsilon. Okay, so once we have this, we're going to say let n be greater than m. So 1 over n is going to be less than 1 over m. Thus 1 over n, actually I should put it's less than 1 over m, which is also less than epsilon, right? So 1 over n is going to be less than epsilon. And our conclusion is going to be thus for all real epsilon greater than 0, there exists an m belonging to the set of natural number such that for all n belonging to the natural numbers, we have that if n is greater than m, it implies that 1 over n is going to be less than epsilon. Yeah, and that is it for item G. So once more, all we have done here is that we have proved that if epsilon is greater than 0, it means that there exists a natural number m such that for all natural numbers n greater than m, we have that 1 over n is less than epsilon. So that's it for item G. And let's do item H. Okay, so for H, we're going to have something that's very similar. We're going to have that for every real number epsilon greater than 0, there's a natural number m, such that if little m is greater than n, which is greater than capital M, then this stuff here is true. So what we're going to say here is let epsilon belong to the set of real numbers and epsilon be greater than 0. And then we're going to say suppose that for little n, capital M being natural numbers, suppose that this happens and that capital M is going to be greater than n, which is going to be, little m is going to be greater than n, which is going to be greater than capital M. So n is greater than m. Well, using this, we have shown previously in part G that if n is greater than capital M, if this is true, then this is our conclusion, right? And so we have that this is true. Thus, by part G, we have that 1 over n is going to be less than epsilon, right? And so let's just see the implications of this. So m is going to be greater than n, which is greater than capital M. So when we divide it, we're going to just reverse this, right? So 1 over m, and actually I should say that little m is also a natural number. So 1 over little m is going to be less than 1 over little n, which is going to be less than 1 over m, right? But 1 over little n is less than epsilon. So we have that 1 over m is less than 1 over n, which is going to be less than epsilon, right? So what I'm going to do here is I'm just going to say that I'm going to subtract 1 over m from this side, and I'm just going to say thus 1 over m minus 1 over n, since 1 over n is positive, is definitely going to be less than epsilon. Since 1 over m is less than epsilon and 1 over n is positive, it means that 1 over m minus a positive number is still definitely going to be less than epsilon. And so we have proved it, right? And thus, for every real epsilon greater than 0, we're going to say there exists an m belonging to the set of natural numbers such that if m greater than n greater than capital M, then 1 over n minus 1 over m is going to be less than epsilon. And that is it for item H. So for item I, what we have here is there is a natural number k such that 1 over r squared is less than 0.01 whenever r is a real number larger than k. So actually this is a conditional if p then q, where this is our p, because we have q whenever p, right? So that is going to be our assumption, that we'll assume that r is real number larger than k, and then we're going to prove that the conclusion happens. So for I, we're going to say let r belong to the set of real numbers, and we have natural number k, and k belong to the set of natural numbers. Suppose that r is larger than k. Suppose that r is going to be larger than k, right? So what we're going to say here is we're going to say we would just want to show that there is a natural number k. So we're going to say let k is equal to 10, because we just have to produce an object in the universe. And so if k is equal to 10, we have, note that r squared is going to be greater than k squared. So r squared is going to be greater than 100, which is k squared. And what we're going to do here is just then divide both sides. So 1 over r squared, we're just going to take the reciprocal. And if it's greater than 100, the reciprocal is definitely going to be less than 1 over 100. Thus, 1 over r squared, 1 divided by 100 is 0.01. And so we have proved it. So there is a k belonging to the set of natural numbers such that 1 over r squared is less than 0.01 whenever r belongs to the set of real numbers and r is greater than k. So that is it. We have shown what we needed to show for item I. Let's do then item J. So for item J, we want to show that there exists integers L, G such that L is less than G, and for every real number x, if x is between them, then this thing over here is true. So we're going to say let L, G belong to the set of integers, and let L be less than G. And since we want to just show that there exists, we're just going to choose 2 from that universe, from the universe of integers. So I'm going to say let L be equal to negative 15 and G equal to negative 1. Now we're going to say, suppose that there exists an x between them, then we have to show that this thing here is true. So let x belong to the set of real numbers, so let x belong to the real numbers, and let x be less than G but greater than L, right? Then x is going to be less than minus 1, which is going to be greater than negative 15. So once we are here, I'm just going to reverse this inequality. So I'm going to multiply everything by negative 1. So 15 is greater than x, which is greater than 1. So once we're here, what we're going to do is multiply everything, and that should be minus x. We're going to multiply everything by 2. So 30 is greater than negative 2x, which is greater than 2. And then what we're going to do here is just add 10 to both sides. So 30 plus 10, which is 40, is greater than negative 2x plus 10, which is greater than 2 plus 10 is 12. And so we have shown that this thing is true, right? So what we're going to say is, therefore, there exists LG belonging to the set of integers such that for all x belonging to the set of real numbers, if x is between L and G, so if x is between less than G, greater than L, if this is true, then 40 is going to be greater than minus 2x plus 10, which is going to be greater than 12. So that is it. We have proved item J. So now let's do item K. And we want to show that there exists an odd integer m such that for all real numbers r larger than m, 1 over 2r is going to be less than 0.01. So we're going to say let m be an odd integer, right? So let, that is item K. Let m be an odd integer. And we're going to say let r, oops, that should be little r. So let r be a real number such that we're going to have r is larger than m. So what we just want to show here is that there exists an odd integer m, right? So we're going to say let m be equal to 51, because 51 is an integer and 51 is odd. So what we're going to say here is that then r is going to be greater than 51. So what we're going to do is we're just going to multiply everything by 2. Then 2r is going to be greater than 102. So 1 over 2r is going to be less than 1 over 102. And let's see, 1 over 102, so 1 over 2r, 1 over 102 is going to be, let's see, 0.0098, and this is less than 0.01. Thus, we have that 1 over 2r is going to be less than 0.01, which is what we wanted to prove in the first place. So our conclusion is going to be, thus there exists an odd integer m such that for all real r's greater than m, then m, we have that 1 over 2r is going to be less than 0.01. And we have shown that this is true when we choose that m is equal to 51. So that is it for item K. So for item L, we want to show that for every natural number x, there exists an integer k such that 3.3x plus k is less than 50. So what we're going to do here is we're going to say L, let x belong to the set of natural numbers, and k belong to the set of integers, right? So x must be greater than 0 because it is a natural number. And then we're going to say let k be equal to negative 4x. Since x is a natural number, minus 4 times a natural number is an integer, right? Then we're going to do note that 3.3x plus k will be equal to 3.3x minus 4x, which is going to be equal to negative 3.3, so negative 0.7x. And since x is positive, I'm going to say we have that negative 0.7x is less than 0, right? Because x is positive, so this product has to be less than 0. So negative 0.7x, if it's less than 0, it's definitely less than 50, correct? Therefore, 3.3x plus k is less than 50. And so we have shown that it exists. And so our conclusion, thus, for every natural number x, so for all x belonging to the set of natural numbers, there exists k belonging to the set of integers such that 3.3x plus k is going to be less than 50. And that is it for item L. Now let's do item M. So item M, we want to show that there exists x less than 100 and y less than 30 such that x plus y is less than 128. And for all real numbers rs, if r greater than x and s greater than y, then this inequality here is true. Okay, so we're going to say let x, y belong to the set of integers. And then we're going to say let x be equal to 99 and y is equal to, let's see, I'm going to call that 28. Okay, So we have that, x is going to be less than 100, right? Because 99 is less than 100, and y is less than 30. So what we've done here is that we've shown that it meets this criteria, and we have that x plus y and x plus y is going to be equal to 127. So x plus y is going to be less than 128. So we have shown this. And now we want to show that for all real numbers Rs, so we're going to say let Rs belong to the set of real numbers, and let, we want to have R greater than X, so let R greater than X, and S greater than Y. And we want to show here, so we've taken care of that, we want to show that then this is the conclusion, right, that this happens. Okay, so if this is true, then R is going to be greater than 99, right, because X is equal to 99, and S is going to be greater than 28. So if we have this, thus R minus 50 is going to be greater than 99 minus 50. So R minus 50 is going to be greater than 99 minus 50 is going to be greater than 49. And I have that S minus 20 is going to be greater than, because S is greater than 28, right? So it's going to be greater than 28 minus 20. So S minus 20 is going to be greater than 28. So we're going to take these facts here. Let me just highlight them. We're going to take this fact and that fact to show, thus, R minus 50 times S minus 20 is going to be, oops, that's not 28 here on the side. Actually, it should have been 28 minus 20 is going to be greater than 8. And this is going to be greater than 49 times 8. So R minus 50 times S minus 20 is going to be greater than, let's see, 49 times 8 is going to be greater than 392, which is greater than 390. And so our conclusion is going to be, therefore, R minus 50 times S minus 20 is greater than 390, for X is equal to 99, Y is equal to 28, R greater than X, and S greater than Y, and X plus Y less than 128. Actually, I shouldn't even, yeah, just that. So we have proof that this is true, and then the conclusion, you would rewrite this whole thing. You would say then, therefore, there exists integers x less than 100 and y less than 30, such that, and you would conclude the whole sentence. I'm just not going to write that because that's going to be super long. And that's it for item M.